So this is workshop 3, part 2, video talkthrough. So at this point we've generated our time series and we've got a script which does that, called createTimeSeries.m. Now we're at the end of step 2. It says, given your time series, what do you expect the Nyquist frequency to be? Well, we've got our sampling interval dt, which is 1 over 10, and we know our sampling frequency is 10 samples per hour. So our Nyquist frequency, we expect that to be half of our sampling frequency. So we would expect that to be 5 samples per hour. So in other words, when we generate our spectrum, then the peak or the maximum limit on the frequency axis will be the Nyquist frequency, which should be 5 samples per hour. Okay, it's also asking what is our frequency resolution. Frequency resolution relates to the duration of the time series. So we've got a sampling time of 60 days. So our the lowest frequency that we can resolve will be 1 divided by 60 days, which if we put in terms of hours, so 1 over T max. We should expect then that the spectrum that we generate will have a resolution of 6.9 times 10 to the minus 4 on the frequency axis. So every point on our spectrum will be separated by frequencies of 1 over T max. Okay, and that will also be the lowest frequency that we can resolve as well. Okay, so it now says step 3, convert to frequency domain using a fast Fourier transform. So I'm just going to show you what the Fourier transform does. Is try this. So y FFT is equal to FFT of y. So y FFT is equal to FFT of y. Use a semicolon at the end so it doesn't, oh, sorry, we called it y0, didn't we? Oh, no, y0. Okay, so the fast Fourier transform returns a complex number. Okay, so if we look over at our workspace, you can see it's called over here complex, which means it's got a real and imaginary part. And the imaginary part contains phase information. We don't actually need that. We just want the frequency information, which is contained in the real part. So now moving on to step 4. Okay, it says plot the real part. So type in plot. This is going to overwrite the our time series plot. We're just having a look at things to see what they look like. That's the aim at the moment. So we're going to plot the real part of y FFT. Okay, great. So that doesn't tell us much at the moment, but the interesting thing is that the output is symmetrical. And so what's happening is that the fast Fourier transform is actually returning amplitudes for frequency components in both positive and negative frequencies. So we actually only need half of this. And because we only need half of it, we can just ignore the other half. But it does mean that we need to multiply the amplitude by 2. Otherwise we will have lost the energy that is been put into the negative frequency. So we can focus on half of the spectrum, the other half is redundant. Now, moving on to step 5, it says open the M file, find psd.m. Let's just close that figure window, we don't need that now. So let's open up find psd.fft. Okay, edit the script so that it is a function that outputs frequency and power spectral density. Okay, so let's do that. First of all, to convert this into a function, we need to get rid of the comment at the top, type in function in front of it, and now we need to give it some outputs. So we want it to output the frequency and also the power spectrum as well. So we put in output PSD Y and frequency. Okay. I don't know if I need that space, I'll get rid of it. So find PSD FFT, and we are going to pass it. We're going to pass it the sampling interval dt, and we're going to pass it our time series y. Okay, and that's all we need at the moment. But what we don't need in here is, because we're passing it the time series y, we can delete the first row where we're actually assigning y to y0, because what we will do is when we call this function, instead of putting y in this position from the command line, we'll put in y0, and it will automatically assign anything that's labelled y with the variable that we've input. Okay, so what does this do? So this is, it defines the length of our time series, which is going to be the length of y, or y0, which is what we're going to input. This is our sampling frequency, fs, so let's just put a comment in so that we know what this is. Sampling frequency. Okay, and then this is what we've just generated, the fast Fourier transform YFFT. And what we want is the power spectral density, because that's the conventional way of plotting frequency spectrum. So we find the power by squaring the amplitude here. So we take the absolute value because we don't want to have the complex components. So taking the magnitude, squaring it, and then we're normalizing it by the length of the time series divided by n. And then, because the function is symmetric, we'll need half of the length of YFFT, and we need to multiply it by 2. So the first command here, or this line here, p equals p of 1 to n over 2 plus 1, that's defining the first half of the time series. And then we need to multiply those frequencies which are repeated in negative frequencies, we need to multiply those by 2. The ones that we don't multiply by 2 are the Nyquist frequency and a frequency of 0, because those don't occur twice in the time series. It's just the ones that have got both positive and negatives. So we go from the second data point up until the last minus 1. Okay, so we haven't defined end. No, we don't need to define end, sorry. So we go from the second data point up until end minus 1, and we're multiplying it by 2. Okay, and then in order to get the power density, we divide by the sampling frequency, and so this gives us PSD y, which means power spectral density of y is equal to the power divided by the sampling frequency. And then we can define our frequency axis as well, which is defined like this up until the Nyquist frequency, fs divided by 2. Okay, so now we can save that, and that should now be a function that we can call from the command line.